Okay, so sorry about that interruption, but it's important to find out what the biggest terms are, and that's because they all behave a similar way. So if you remember a line always begins in quadrant 3 and ends in quadrant 1. So this is quadrant 1 up here. This is quadrant 3 down here. And this is important to note that these are all the positive when it's positive in front. I'm only going to deal with the positive first. Now, a line has a power to 1. Y is equal to x is the same as y is equal to x to the power of 1. So it's important to keep that power in mind. It's still 1. And is 1 odd or even? 1 is odd. So we're going to find this consistent pattern between odd-powered polynomials that are all going to start in quadrant 3 and end in quadrant 1 if they are positive in front of them, like positive 5x will still follow this rule. We'll get into what minus 5 would do. But here's a line. Now let's look at a cubic. A cubic will start in quadrant 3, come up, and then go up like this, and end in quadrant 1. And you always read graphs from left to right. So as x increases, what happens to the y? It goes up and up and up from quadrant 3, quadrant 1, and happens to enter through origin as well. Let's look at a x to the power of 5. I'll do that in blue. It can do this, and actually I should go back to the 3 because the 3 can also do this. Go up, come down, go up. And I'll get into the significance in a second. What can x to the 5 do? X can go, also starts in quadrant 3, can go up once, can go down once, can go up once, can go down once, and then goes up. Now let's discuss this. How many turning points in this cubic? And turning points is how many times does the graph change directions? Well, there's 1 and there's 2. Those are the turning points. It changes directions twice. How many turning points in that straight line? 0. So you're going to discover the number of turning points, and this is important, is 1 less than the power. So a line, which is x to the 1 less is 0, which explains why it has no turning points. And x to the power of 3, how many turning points can it have? Turning points, 2. And that's up to 2. You can find sometimes they don't have a turning point. They just do a weird wiggle, but that's a maximum of 2. So you can see it's related to their power. Now, let's also look at how many times they cross the x-axis. Well, a line crosses the x-axis once. So that means it can cross the x-axis once, and that's equal to its power. What about a 3? Well, you're going to discover that a triple can cross the line once, twice, or 3 times. So we're really looking at the maximum. And we'll keep in mind that it will at least cross once. You'll notice that odd powers, so x to the 5, have to at least cross once. But the maximum times they can cross the x-axis is their power. So that's the interesting rules that you have to write down. So for odd number polynomials, they all start in quadrant 3 and in, so start in and end in quadrant 1. They all have a bend up to the 1 less than their power. Okay, so that's the second point. They can cross the x-axis, or they must cross the x-axis 1 time at least, and up to the number of their power. So a cubic can cross 3 times. And this is important. It's slightly different than evens. Evens don't have to cross the x-axis, but odds have to cross the x-axis at least once and have to do this. They all have a turning point up to one less than their power. So an x cubed, a cubic, can have 2 or 3 turning points. an x to the 5 can have 1 or 2. It should have been 1 or 2, one less than their turning point. Can have 1, 2, 3, or 4 turning points, one less than its power. We'll get into how it only has 1 later on, but if you put in the basic parent graph x to the 5, you'll kind of see how it has 1. So this is something you should memorize. You should also memorize that these turning points are when the slopes are going to be, the slope of their tangent is going to be 0. And Desmos is great for illustrating this. So I'm going to show you a normal line first. There's the line. Then I'm going to show you the normal cubic x to the power 3. Now here's how it only has 1 turning point, or actually no turning points. And it only crosses the x-axis once. Now you might say that's not a turning point, but it kind of does a double wiggle there. And so, I mean, technically it flattens out and then continues. Let's look at an x to the power 5. It's going to look very similar to that. You might say, well, I don't really see a difference. Well, it's only when their roots start getting slightly different, like x. If I do x minus 1 here, or x plus 2, x minus plus 1, and x, then you will see a slightly more wiggles. See? And this is a cubic, because if I multiply out all their x's, the biggest power I'm going to get is x cubed. And this is how you know it. There's one x, there's another x, there's another x, and they're all multiplying, so that's x to the cube. And see how it has 3 x-intercepts and only 2 turning points. Very important. And you can do this the same with x to the 5. I'm just going to add some more x-intercepts to it. I'm going to make the opposite side x minus 2. And this is a power of 5. It's got 1, 2, 3, 4, 5 x-intercepts. It starts in quadrant 3, ends in quadrant 1, and it has 1, 2, 3, 4 turning points. And this is very important to understand. Now let's look at evens. We're very familiar with the standard parabola. And you might say, oh yeah, parabola. But you know, parabolas have an interesting thing. They don't have to cross the x-axis. But I want you to notice even. It starts in quadrant 2 and it ends in quadrant 1. So now we're on to evens. Even-powered polynomials. Here's the rules that you'll have to memorize. Start in quadrant 2 and end in quadrant 1. This assumes a positive coefficient in front of the largest power. And what are some evens? Well, x to the power of 2, x to the power of 4, x to the power of 6. The even number is their power. And that would be the largest, whatever the largest term is. That's where you look. So that's the first rule. Starts in quadrant 2, ends in quadrant 1. They can cross the x-axis 0 times and up to the number of their power. So an x to the power of 2 can cross 0, 1, or 2 times, which you're already familiar with. This is the same rule for x to the power of 4, though. X to the power of 4 can cross 0, 1, 2, 3, or 4 times the number of its power. Now finally, their turning points will be 1 less than their power. So an x to the power of 4 can have, I guess technically 0. I mean, I still call it 1 turning point, 2 turning points, or 3 turning points. Let's look at it. Let's look at a few. So there's an x to the parabola that's raised to 4. It never crosses the x-axis. If I lower it by 4, it crosses the x-axis twice. And if I have nothing here, if I have no b value here, it only touches the x-axis once. Let's look at a power to the 4. So the basic one looks like it only turns once, right? It touches the x-axis once. If I add 3 to that, it touches the x-axis never. If I subtract 3 from that, it touches the x-axis twice. But you might say, well, you said it could touch the x-axis up to 4. Yeah, we do the same thing as we did before. We do x plus 2 times x plus 1 times x minus 1. And here we can see it. And you might say, well, that doesn't touch cross 4. Well, we're going to just subtract that by nothing. And we can see it crosses once, twice, 3 times, 4 times. And we can see it has 1 turning point here, 2, 3. So here we can see it. Now if I raise this whole thing by 4, it doesn't cross the x-axis at all. If I lower it by 4, it's only going to cross the x-axis by 2. So these things all vary, so you have to understand what you're looking for. And graphing technology helps. But all of these things, I'm going to add 2 more for an x to the power of 6. There's an x to the power of 6. And it crosses once, twice, 3 times, 4 times, 5 times, 6 times. How many turning points does it have? 5. 1, 2, 3, 4, 5. So you just have to be aware it can have up to 5 turning points and up to 6 x x-intercepts. But if I just do the parent graph, x to the power of 6, it only crosses the x-axis once and has 1 turning point. And if I raise it by 3, it doesn't even cross the x-axis. And that's because these even polynomials have the power of not having to cross the x-axis because they stay in either quadrant 2 or quadrant 3. Now let's look at what happens when I take an example that I have, like that one, and put a minus right out front here, big old minus. The whole thing turns upside down. Suddenly it starts in quadrant 3 and ends in quadrant 4. So this is an important distinguishment. If your largest power has a negative in front of it, the whole starting process will flip. It'll all flip in the x-axis. The same rule for turning points applies, but where it starts is quadrant 3 and quadrant 4. What do you suppose will happen if I flip like a normal line? If I flip a line, what will happen? Well, we flip in the x-axis. Suddenly, instead of starting in quadrant 3, we start in quadrant 2 and end in quadrant 4. So I want you to be aware. Now watch what happens when I put it to the power 3. Same rule. It starts in, when it's got a negative in front of it, it starts in quadrant 2 and ends in quadrant 4. So these behaviors are something you need to learn. And you also need to learn that at their turning points, the tangent, the rate of change, will be 0. This plays an important role in this chapter and in calculus. All right, let's look at the book. So they go through, they want you to understand quadratic, cubic, quartic, that's a power to 4. Quintic is power 5. They also want you to understand the key ideas and be able to identify it from the graphs. And then they want you to further your understanding. So they want you to identify from the graph. Notice I skipped basic skills in this one. I don't think we need it, but I can go back later and cover it. There's a couple of things I still have to cover from the last chapter too. But let's look at this. How many turning points does this have? 1, 2, 3. So I would say that's at least an x to the power of 4 because it's got 1 less turning point. It also crosses twice only, but that's fine. But notice it doesn't start where it normally does in quadrant 2 and end in quadrant 1. It starts in quadrant 3 and ends in quadrant 4. That means its largest power has a negative in front of it. It might be -5, it might be -2, it might be -1, just the negative, but it has a negative because its starting point and ending point are reversed, and because it has 3 turning points, I'm going to say it's to the power of 4. What about this one? Well, this one is not a polynomial at all. It's a growth curve. And actually, they're just asking us whether it's polynomial or not. This is a growth curve. It is not a polynomial. What about this one? This is obviously a root function. It is not a polynomial. What about this one? Well, I can see 1 turning point, 2 turning points. So this is a polynomial. And it's an x to the 3. And I'll say, well, it starts in quadrant 3 and ends in quadrant 1. So it has a positive in front. You can even figure out the roots there. There's one x root. There's another x root. And there's another x root. So I can even figure out that this one is an x plus 2 x plus 2. It's an x plus 1, and it's an x minus 1. What factor it has in front of it, I don't know. We'd have to put one plot point into here to figure out what its a is in front, but I do know its a is positive because of where it starts and where it finishes. So these sorts of analysis will just make your calculus life and your functions life easier. What about this one? This is clearly a parabola, and it's upward facing, so it is a function. That was a function as well. And it is also be noticed as a parabola, and since it faces upwards, it's got a positive. And this is obviously a sine curve, so it is not a polynomial. So they just want you to get used to spotting the graphs and recognizing the graphs. Determine which one of these is a polynomial and type and why. Well, that doesn't have any roots or anything in it, so it's got 3 terms. It's a cubic, and it's positive, so it would start in quadrant 3 and end in quadrant 1. This has an x squared, then a 3x minus 2. That is indeed a polynomial as well, and it is a parabola. This is also polynomial, and it is a line with a slope of 2 and a y-intercept of minus 7. This is not a polynomial. It is a root function, and it's been shifted to the left by 1. This is a rational function. We could even factor the top to figure out more about it, but it is not a polynomial. And this, finally, you might be fooled by it and think it's a parabola, but when we expand this bracket, that just means this times itself. We will get an x squared, and then that'll be multiplied by this x, so we will get an x cubed. So this is actually a cubic. It will also have a positive in front of it. Use finite differences to determine the type of polynomial functions that could model each relationship. So finite differences is a very useful skill. It helps if those tables are on the side instead of the way they are. But it also helps if your x values go up by the same amount each time. And I want you to keep that in mind, that your x values will go up the same amount each time. So sure enough, these x values are going up by plus 500 each time. So that's fine. Let's look at how these y values are going up. This one's going up by 25. This one's going up by 25. This one's going up by 25. And this one's going up by 25. If your first degree, this is called the first difference. So when you do your first difference, if they are all the same number, it is a line. Since first difference is same number, it's a line. And we can now figure out what kind of line that is. Mx plus b is the formula. If we could, can we figure out the m? Yeah, delta y. So let's take 225 minus 200 divided by the same delta x, 500 minus 0, which is 0. So we get 25 over 500, which is the same as 5 over 100, which is the same as 0.05, which means the m over here is 0.05, or you could even have the fraction 5 over 100. Actually, we can simplify that, 1 over 20. So that means its slope is 1 over 20. And do we have a b? Well, fortunately, the b is right in the equation. When x is 0, y is 200. The y-intercept is shown right here. When x is 0, y is 200. That means the b here is 200. It's also going up and up, positive, so the slope is positive. So we will have a line like that that has a very gentle slope and crosses the y-axis at 0, 200. So right away, first differences tells us a lot. This just even how this is described should tell you we're not going to get a line. So this is going up by 1. So that means my x values do indeed go up plus 1. Let's look at our y values. This first one goes up plus 15. This next one goes up plus 5, already shrinking. This next one goes down minus 5. And this next one goes down minus 15. Are those the same? Not the same. Not a line. That's your first thing. Now you've got to take what's called second differences. That was first differences. When your first differences are not the same, you keep going. So what's the difference between 25 and plus 5? It's minus 20. What's the difference between plus 5 and minus 5? It went down minus 10. What's the difference between, oh, you know what? I got this first one wrong. That's plus 15. There we go. So that'll affect it. What's the difference between plus 15 and plus 5? It went down 10. What's the difference between plus 5 and minus 5? It went down 10. What's the difference between minus 5 to minus 15? It went down 10. So we have the same second difference. Therefore, it is x to the power of 2. Or in other words, a parabola. And that's how you figure it out. Now, if you keep going, if those were not the same, and you were to keep going and you were to go down to the next line, if the third differences... Yeah? Yeah, I'm busy. The third differences are the same. We're dealing with a cubic. And so on. If fourth differences are the same, we're dealing with x to the power of 4, so on. But now we're dealing with a parabola, and we can even use the parabola formula, ax squared. And technically, you'd have to put in ax minus k. But we should be able to figure it out with ax squared plus b. Well, they gave us the b right away when x is 0. Y was 10. Now, all we would have to do is figure out the a. And to do this, we would take any value of y, where we have a value of x. So when y is 25, x is 1. What's 1 squared? It's just 1 plus 10. So that means 25 is equal to a plus 10, which means a is equal to 15. Now, the question is, did we get our proper a? And that, because it would imply that the equation is y is equal to 15 x squared plus 10. And that's just that's telling me it's an upward facing parabola. I don't buy that this is an upward facing parabola because it's going downwards. So that means I probably did something incorrect. When x is 1, y was 25. Yeah, I don't buy, I think it's a downward facing parabola, which means I probably put in an incorrect value here. And actually, you know what? This is the vertex formula. I should be using this formula. My mistake. This is where I screwed up. How many variables am I missing? I don't know A, I don't know B, but I know C. C is 10. Then I take it for the next value. On the next value, I have 25 is equal to A. 1 squared is 1. Plus 1x, or bx is just b, plus 10. So right away, I can simplify that. I say 15 is equal to a plus b. And I can immediately say a is equal to 15 minus b. So now I have a value for a, but not specific. I need b. Then I do the next line. The next line, when y is 30, x is 2. So I get a. What's 2 squared? 4. So it's 4a plus 2b plus 10. And then when I isolate this, I get a new thing, and I get 20 is equal to 4a plus 2b. But I just had an equation up above for a. So I'm going to replace my a with this. And I get 20 is equal, I expand that, 60 minus 4b plus 2b. What's minus 4b plus 2b? Minus 2b. Okay, so now I get minus 2b is equal to minus 40, which means my b is equal to 20. If my b is equal to 20 and a is equal to 15 minus b, then my a is equal to minus 5. Now I have the proper equation, and the proper equation is y is equal to minus 5x squared, which makes more sense now, plus 20x plus b. So my bad was I was using the vertex formula, and that threw you off. Now that's how you can figure out an equation, when you know first or second differences and the base equation. But the more missing variables you have, the more equations you need. If you're missing 3 variables, you need 3 separate equations. If you're missing 2 variables, 2 separate equations, and so on. And it didn't ask me to do that. All it asked me to do was determine the type of relationship, and this is a parabola. So it is a downward facing parabola, which makes sense because this rocket goes up and comes down. When I go on here, it's asking me to look at the volume of a box. Now, right away, you should note, you should get a hint from that. These are, and I'm not going to do the formulas anymore. I'm just going to do first and second differences. But the hint here is that if you're dealing with volume, volume is width times depth times height. Well, right away, I can tell you that's going to be a cubic. But we're going to just put this down. And we'll notice our first differences of x are going up by 1. And then when we look at our first differences here, it's plus 25, plus 25. Oh, that's interesting. Oh, I see. It's saying the volume of a box varies at different widths. So that's just saying, based on the width, the box, since it's probably a perfect box, it will go up consistently. So this is a same. So same first differences, which means we're dealing with a line formula. Width, volume is based on width times something. Now you might say, well, that doesn't make sense, and you'd be right. If I was looking at volume times width times length times height, then we'd be dealing with a cubic, and we wouldn't get this result. But this is saying the volume of the box varies at different widths. As the width increases by 1, the volume's increasing by 25, so that's a direct relationship between the width and the volume, which means that the volume is that length and height are the same. So that makes sense that since these are the same, that the width times the same value would be a straight line. And you could figure out what the value is. If you notice, you might say, well, we don't have a y-intercept, but if you go backwards, your y-intercept is indeed going to be 175. And you just need to figure out your slope, and you'll instantly see that the slope is 25 over 1. So this would be your relationship. So the volume would be 25 times the width plus 175 will give you the volume over and over again. If you plug that in, you'll see that's true because it was a straight, direct relationship. So the type of function here, this is a line, and it's a polynomial. What about this one? What's going on with this one here? These are indeed going up by 1, so that's good. Now let's look at the first difference here. It goes up by plus 4, and right away we can see it's not the same. It goes up by plus 28. Then it goes down by negative 14. Then it goes down faster. It goes down by negative. It goes down very fast. 44 plus 8, 52. Then suddenly it goes down by 244, etc. Oh wait, it suddenly went up. So we have something that's going up and down and up and down. And this wasn't down, which I thought it would be. This was up. So it goes up and up. Oh, sorry, I got this wrong too. That's still going up. 70 plus 76. And this is going up by 152. Oh, wait, yeah, so it's just going up and up and up and up. This is going up by 244. And this is going up by 364. So right away, first differences are not the same. Let's look at second differences. So it's not a line. Second difference, plus 24. Plus 46, 48. Plus 30, 80. So 76, I think. Then plus 100 and minus 8. That'd be plus 100 minus 8, so 92. and then plus 120. Now that's not the same numbers, so sometimes you have to give up and realize something's going on, but let's keep going. This is plus 20. That's plus 28. Plus minus, that's plus 20 minus 4, so that's plus 16. And that over here is plus 28. Now I don't know if I think I might have screwed one of these up. And it's not making sense. So if I do the next one, yeah. So when I see this, then you've got to start saying what's going on. Will I get the same first differences? So this is plus 8. And then this is, if I got it right, this is negative 12. And then suddenly, just doesn't seem like I got that first one right. So another good way when you get stuck like this is go to Desmos. And I think I just did a fatigue error there. But anyway, you can put in a box, and you just put your y values. And you can see you're dealing with a growth curve. And an interesting thing about Desmos is if you think you're dealing with it, you can just put it, and I don't know what the base would be, and you can use this symbol and ask it to figure it out. Would help if you sort of knew the base. And you can just say plus k. And you can hope it figures it out. Now if it doesn't figure it out, you probably didn't figure, to the x to the 1 here. There we go. So you can see that it's saying that it might be this curve, but that doesn't quite fit. You could say that we have a plus 200 here. Yeah, it's looking like some of these values fit. But if you think it's a, half a parabola, you can do this as well. Unfortunately, it gave me the y value up there. And you can ask it to figure it out. It's having trouble with it. I don't know why it's having trouble with it. I think because it's saying it's not a y1 here. There we go. And that doesn't quite fit, right? So there's all sorts of issues going on here. But it's clear that that doesn't quite fit. I think if I did those first, second differences more properly, I could have figured out what's going on. So I think I just had incorrect calculations. I should try it again because I know you can fast forward past this if you want. Okay, so I'm going to just try it again. Plus 4. Wow, it really jumps. Plus 28. Plus 76. Oh, okay. I think I made an error in there. Plus 148. And then plus 344. Okay, the next one. Plus 24. You can always divide one by the other and see if you're dealing with a growth curve. This one's plus 48. Yeah, I think we're dealing with a growth curve. And this one's plus, if this one says plus 96, we are. Nope. So 72. That's, did I do it wrong again? See? My brain's not working. That was the difference between these two. This is 244. Okay. And this last one is plus 96. Interesting, it's close. And then I get 24, and notice the numbers are repeating again. 30, so 26, getting closer. And then, oh, 34, 24. Ah. Then plus 2 and then minus 2. So I would say that this is not a function. It'd be great to keep analyzing it, but I see these numbers are flipping back and forth. So I do not believe that's I believe that's a growth curve of some kind. I probably botched that. Sorry, I should have gone back and checked that one out. Graph this function to the power of x on the domain 0 to 3. Explain why a person who sees only this graph you created, not the equation, might think this graph represents a polynomial. There's not enough information. Explain why this function is not a polynomial function. Because it doesn't fit within our rules. It's not a x term with an exponent. Draw a graph of a polynomial function that satisfies all the following characteristics. Oof. Okay. So very tired, so I might not get this one correct. But let's start with what we know. So when x is minus 3, y is 16. That's the first thing they tell us. When x is 3, y is 0. When x is minus 1, y is 0. So putting that in order, this would be the correct order, which it helps. Then they tell us the y-intercept is 2. Y-intercept is 2, so that might help. And when x is smaller than 0, the results of y are smaller or equal to 0 when x is bigger than 3. Okay? So y is negative when x is bigger than 3. The domain is the set of real numbers. That's fair enough. Well, first of all, this is going up by 2. Oh, I still have it in the wrong order. This is not quite enough information because my x values are going up by 2 and then 4. And we can see that I get a 0 twice. So that's interesting. That means I cross the x-intercept here, and then they give me the y-intercept down there. And if I'm going to draw it, so I know it crosses the here. So just always put in the points you know. So minus 1, 0, it's going to cross the intercept here, and you would label it. And then 3, 0. We know it has a y-intercept that is at 2, so just barely here. And we know that when y is minus 3, it's way up here. So just drawing it, there could be a couple things going on. You could have this. Okay? And notice that we have a y value. And so it would imply everything up to here is the y is negative, so this part makes sense. Which means, since we don't cross the y, well, they don't tell us if it does it again. If it could cross the y-axis multiple times. But based on the information, we have something like this. And it doesn't really tell us more than that, except that we have this one point up here. So if I'm going to draw it, I'm going to say I have 1, 2 turning points, and I have 2 x-intercepts. But based on that turning points, I'm going to say I'm dealing with a cubic. It starts in quadrant 2 and ends in quadrant 1. So it's a cubic with a minus in front of it, because most cubics start here. And that's all I could say with the information provided. Oh, there's one more. When x is smaller than equal to 0, so when x is bigger or equal to 0, oh yeah, y is positive. Wait, y is positive? Yeah, y is positive when x is smaller than 3. So it could even come down here and then come back up, and they didn't tell us. So there might be a dip here. And then when x is, y is smaller than 0 when x is bigger than 3. So they didn't really... Oh, okay, they're saying everything from the left of this point, y is positive. So fair enough. So it does not cross the y here. So that is indeed a graph of it. If you were going to graph that, again, you've got what information? You've got minus 3 is equal to 16. Three is 0. Do that there. And you've got the other one, minus 1 is equal to 0. And those are your main points. And then finally you have when x is 0, we've got one other point. When x is 0, the y-intercept is 2. So we can put that there. 0, 2, and 3, 0. And the rest of the stuff you get rid of. Okay. And then it drew it based on a cubic, or on that, but I'm going to draw it based on a cubic. So I would do that. And sure enough, it's drawn it properly for me. There it is. And it meets all the criteria that were just described. And it gives me my likely A value, my likely B value, and my likely C value. Now I think you could also derive this from the data given, because you have 4 points. So 4 points is enough to figure out 3 missing variables. But just by graphing it, you've answered the question. Explain why there are many different graphs that fit combinations characteristics in question 5. Well, draw 2 graphs that are different from each other and explain how they satisfy the characteristic number 5. Well, if they don't tell us all the values that cross the x-axis, that's one information. We know it does indeed cross the x-axis, but you could have something like this that we don't know. So you could have this. You could meet all the criteria, but from this point here, you could have a couple wiggles. And there, and even on this part, you could have a couple more wiggles, so long as it doesn't cross the x-axis. So there's always a few more turning points that could exist that we're not told about. The only thing we're for sure are these 4 points. Create equations for linear, quadratic, and polynomial that all share the same y-intercept of 5. That's y-intercept of 5. So that's essentially doing it like this. So here's a line with 5. Here's a parabola. Doesn't matter what I put for the parabola, so long as I have plus 5. Okay. Here's a cubic. So long as I have plus 5. Here's a quadratic. Plus 5. And I could come up with a million of them. But notice they all share the y-intercept. Notice their commonality. There you go. I would skip this. I don't like, I mean, if your teacher wants you to do it. And then they're going to go into the things we discussed. And I would like to maybe touch on what they're going over here in the beginning of your skill sets. And the reason they do this expansion is because later on you're going to get better at simplifying it, but they also want you to be able to identify the biggest term when you expand it. So definitely practice expanding it so you get used to, for instance, I can tell you this will end up the biggest term, x cubed. This will end up being x cubed. This will end up being x squared, and this will end up being x cubed, and they want you to get used to it. Factor, they want you to get back good at factoring with good reason. Remember that you would factor out a 2 from this one before you solve it, right here, of all of them. Solve each of the following equations. So you notice there's only one missing variable. So in this one, it's 2x is equal to minus 12. Therefore, x is minus 6. In this one, you would expand it. Oh no, x is either equal to minus 3 or x is equal to 9 divided by 2 for it to be true. This one you would factor it. A number that multiplies out to 24 and adds up to 11 is 3 and 8. So you end up with x plus 3, x plus 8. Therefore, x is equal to minus 3 or x is equal to minus 8. And this one, when you factor out, I believe you can factor out 2. You get 3x squared plus 11x is minus 8. Or minus 4 is equal to 0. Then you'd have to just factor. You have to get this 8 over to the left side. You have to factor out a 2, and then you can solve it. And I'm not going to bother. Describe the transformations. We've got a graph that is compressed by a quarter and translated upward by 9. And we have a graph that is also moved to the right by 3. In here we have a horizontal stretch by a factor of 2 and a vertical translation downwards by 7. The equation here is y is equal to a, x plus x minus 4 in brackets, x minus 6 in brackets. And I believe you could figure out the a by plugging in the vertex down here. This vertex you could also write in vertex format and figure it out. Here is an upside down parabola that has a y-intercept at plus 3, so it's going to be y is equal to x squared plus 3, and then you would use these one well-known value to figure out the a in it. Graph each of the following. So here this has a vertex of minus 5 comma minus 4, and this you'd have to realize it has a y-intercept, but if you really want to find the information, you should complete the square here. Finite differences, again, very important. And they only want to know if it's linear, quadratic, or other. And then they want you to practice getting this in all 3 formats for parabola. I'd say the only tough one here is getting the correct values for those graphs in number 5. Okay, so looking at it in this one, I know it's x minus 4 and x minus 6, but I don't know the a that's in front until I can take some y values, and you notice the vertex is minus 2 comma 5. So that means when y is minus 2, x is minus 5. So I would get this. When I expand that, I get this. I believe that's right. Oh, no, it's positive 5. So this one would become 1, and this one would become minus 1. So I would get minus a is equal to that. Therefore, a is equal to 2. So if I go back up, I believe that would work. And it works because it's an upward-facing parabola. Then looking at this one, I know it's a downward-facing parabola, so I will expect my a to be negative, but I can't quite see that, but I can see the vertex. So I know my x squared is just going to be normal, and then I'm going to have a plus 4. Now to figure out my a, I need any one clean value that's not the vertex. What's the cleanest point on here? It's probably 2 comma minus 5. So when y is minus 5, x appears to be 2. So 2 squared is that, plus 4. So I'm going to get minus 9 is equal to 4a. Therefore, a is equal to minus 9 over 4. And that's probably somewhat accurate. So minus 9 over 4, x squared plus 4. And if I put that into Desmos, just got to make sure it was plus 4. It's plus 4. And when I go home, there we go. And you can see it's pretty damn accurate to the graph, I believe. Hang on. Yeah, just to the left of 1, just to the right of 1, just to the left of minus 1, just to the right of minus 1. Not bad. Let's see if it indeed has a point down here. There's my point that I think is clean. Looks pretty good. Yeah, that definitely makes sense. So there you go. Hope that helps someone.